Today we're going to talk about a couple of different formulas that are used in the thermochemistry unit to calculate heat. If you'll look at the two equations here, we're going to use both of these. This is heat that you calculate when you're changing temperature, and then there's some heat of formation of a system that you would use when you're looking at a whole reaction. And then we're also going to talk about a third kind of heat, which is heat related to change in phase, like solid to liquid or liquid to gas. Let's look at this first problem, the heat capacity for silver. And then I want to find the energy, which is also heat. So we're going to use the equation Q is equal to mCp delta T. If you'll notice, your Cp is in degrees C, but our temperature is in Kelvin. This is one of those rare times that we don't want Kelvin. We want to have degrees C simply because that's what matched. You could also use calories for instead of joules, and so whatever units that you're given, just convert what you need to convert in order to make all of it match. 25 degrees C. So you have your two temperatures here. Our mass is 150 grams. Excuse me, my pen's not working very well. 0.24 joules per gram degrees C. Our final temperature is 25 degrees C minus our initial. It is important to do final minus initial so that our sign is correct. When you calculate that out, you get 900 joules. However, since you need two significant digits, then you would write it this way. Okay, let's look at a calorimetry problem. A calorimeter is simply a styrofoam cup, typically in chemistry, because it holds in temperature really well. You have a styrofoam cup of room temperature water, and then you have some kind of a hot metal or something else that's hot. You have this hot liquid that you've heated up, and you take the metal and you stick it in the water, and then you put the lid on and you wait for the two temperatures to reach equilibrium so that the temperature of the metal and temperature of the water end up being the same in the end. So the basic equation that you're going to use for this is that the heat lost by the metal is going to be equal to the heat gained by the water. So that's our basic equation that you're using. This is negative because the metal is losing temperature, and this is positive because the water is gaining energy. So Q is equal to mCp delta T. So we could plug that in for each of those. So I like to put a data table over here. We've got data on the metal. The metal mass is equal to 46.2 grams. Our Cp is what we're looking for, and our delta T is final minus initial. Again, the final temperature of both are the same. They both end up at 21.8 degrees C, and then you subtract the initial temperature, and it ends up being negative 73.6 degrees. Now let's look at our water information. We have a mass, a Cp, and a delta T of water so that we can plug them into this equation over here. The mass of water is 75 grams. The Cp, you'll have to look that up on a standard chart. It's 4.184 joules per gram degrees C. I rounded to 3 significant digits, so you might get a slightly different answer if you use all of the digits, but that's okay. Minus 19.6 degrees, and so it's equal to 2.2 degrees C. So what you do is you take each of these and you plug them into the equation. So this mass goes here, the delta T, and when you solve, you get that the Cp of the metal, or heat capacity, is 0.203 joules per gram degrees C. Okay, look at this one. It's kind of like a calorimetry problem. Chloe has some hot water. She adds some cool water to it. She wants to know what the final temperature is. So again, you're going to say that the temperature lost by the hot water is going to be gained by the cool water that she started with. And so you'll have a negative mCp delta T of the initial and an mCp delta T of the final. If you'll notice, they're both water, so our CP of water is going to be constant. Just to simplify the situation, you can cancel those. You can use those in the problem. You're not going to have a problem with that. I just thought I would point that out. Here, there's 20 liters of water. You can convert 20 liters by knowing that water has, you want to find the mass. And so water is 1 gram per milliliter. And then there's 1,000 milliliters in a liter. And so you can cancel those out, and that can give you 20,000 grams of hot water. And our delta T is our final temperature, which we don't know, minus 95 degrees. And then our mass of our cool water, you can use the same kind of calculation, and it ends up being 15,800 grams. We've canceled our CP. Final temperature minus it started out at 75 degrees. So don't forget to distribute. You need to distribute that out. When you solve for T final using your normal algebra that you would use, you get 86.2 degrees C is the final temperature of adding these two waters together. Now let's look at a little bit different. You're not always changing temperature when you're working with heats of solutions. You're also doing, you're changing phase. So you're going to use your CPs, or heat capacities, these are your CPs, when you're doing change in temperature, because you have that formula. However, what about the heat required to change the phase of a liquid? That is much different. So this heat of fusion is the heat required, or energy required, to go from a solid to a liquid, or we would call it melting. And the heat of vaporization is the heat required to go from a liquid to a gas. That's a different kind of heat, because you're not changing temperature. You're actually just using energy to change phase. That energy, by the way, is a humongous amount of energy compared to the other. So don't be confused about that. All right, Anand simply wants to change 1 gallon of water that's already at the boiling point to steam. So this is simply the heat of vaporization. So we're going to use this value, 40.7. It takes 40.7 kilojoules for every mole of water to just vaporize it. That's all we're doing. And he has 1 gallon of water, so we want to go to, we know that there's 18.02 grams in every mole of water, and that came from the periodic table. And then we know our density is 1 gram per milliliter. That's something you do need to memorize. This is an exact number, so it has infinite sig figs. And we know that there is 1,000 milliliters. There are 1,000 milliliters in a liter. And then there's about 3.785. You would need to look this up, liters per gallon. Okay, we're getting closer. And if you'll notice in the problem, it tells us that there's 1 gallon. So we multiply it by 1 because that's how much we have. When we finish, we get that there's 8,550 kilojoules of energy required to boil 1 gallon of water. In this problem, it's a little bit more involved, because we don't just boil the water, because she wants to add the water, change the water to steam. We also have to heat it up first. So there's a portion that needs to be heated, and then there's a portion that just needs to boil the water. And then the total will be the total amount of energy needed to heat it up and then to vaporize it. So if you look at this one, the mass of the water is 521 grams. The heat capacity of water we've used before. And then our final temperature is 100 degrees C minus our initial. The reason we're stopping at 100 degrees, not just because the problem says, but that's where you boil water. So we can't go past that amount until we change the phase. So you get that number. Now the heat of vaporization is given to you as 40.7 kilojoules per mole. How much do we have? Well, 1 mole of water is 18.02 grams from the periodic table. The problem tells us we have 521 grams. Since we have joules up here, we want to make sure that we're adding joules to joules. So we're going to go ahead and say there's 1,000 joules in a kilojoule so that our units will cancel and we'll get numbers that we can add together. When you put that together, you get 1.18 million joules. Look at how much more energy it takes to boil the water than it does to simply heat it up 75 degrees. This is an enormous amount of energy right here. This is huge. Okay, so when you add them together, you get 1.34 times 10 to the 6 joules of energy altogether. Now we're going to look at standard enthalpies of formation. This is where the enthalpy of formation of the reaction is equal to the enthalpy of formation of the products minus the standard enthalpy of formation of your reactants. Okay, so first you would need to be provided with a table that had this information. You don't need to memorize all of these. So when you look at your table, here are your standard enthalpy of formations. I'm going to start with my products because I know that I'm going to be using those first. So I have nitrogen dioxide as a gas. You do need to look at the phase. Liquid water. Then I'm going to use my reactants here, and this is ammonia, gas, and oxygen. Okay. All right, so here's my standard enthalpy of formations. Nitrogen dioxide is 33.2 kilojoules per mole. Liquid water is negative 285.8 kilojoules per mole. Ammonia is negative 46.11 kilojoules per mole. Oxygen is 0 because it occurs naturally. One thing to keep in mind when you're doing this calculation is that you also need to multiply it by the number of moles, okay? Because it says kilojoule, these are in kilojoules per mole, and how many moles of this do you have? So nitrogen dioxide, you happen to have 4 moles. Water, you happen to have 6 moles. Ammonia, you happen to have 4 moles. And you have 7 moles of oxygen, which is still 0. So let's do our equation. Our products are 4 times 33.2 plus 6 times negative 285.8. And I'm subtracting the total of my reactants. So I'm subtracting 4 times negative 46.11 plus 0. Okay, when I calculate that, I get the heat of formation of the entire reaction is negative 1397.6 kilojoules. Now keep in mind that when you're adding and subtracting numbers, you look at the significant digits have to do with decimal places, so you get to have one